Welcome. I am Michael Stewart. Today at the URS Symposium, there's a lot of research being presented, a lot of new concepts being discussed and demonstrated to change the world. Today, I will be displaying my innovation in the way that ray tracing is taught. As an overview, I'm going to discuss the basics of rendering, the prevalence of ray tracing in the industry, why there is a need for my new tool, and I will demonstrate using my new tool. Computer graphics is the field of generating images using computers. Computer programs are becoming ever more sophisticated, enabling entertainment, education, and many other fields to create realistic-looking images. Computers render scenes in 3D using math. In the real world, objects are made up of billions of particles. You see the light which has not been absorbed by these particles reflecting off of them into your eyeball. To describe a scene in a way that computers can understand, objects and models are described using triangles with 3 vertex points. With appropriate software algorithms, computers can process triangles and can compute how they interact with light sources. Lights are then placed in the scene by artists. With these components, the scene can be rendered from a camera's perspective by the computer. The programs that computers use to produce these images can be very computationally intensive. Ray tracing is currently the most popular method of rendering for offline rendering, otherwise known as non-real time, which means multiple hours per frame. Rendering software is capable of producing photorealistic visual results. Pixar has developed one of the industry's most advanced rendering programs called RenderMan. They use it on all of their films. Ray tracing has been a part of RenderMan since Cars in 2006. This technique is responsible for the advancement in lighting within RenderMan. Blade Runner 2049 is the sequel to the very influential film Blade Runner, in which Harrison Ford was the lead back in 1982. His love interest is Rachel, played by Sean Young. The filmmakers have decided for this scene to bring back Rachel as she appeared in the 1982 film, which would be hard to achieve since the actress who played Rachel has aged 40 years since then. To achieve a realistic-looking young Rachel, they have recreated Rachel using stunning computer-generated imagery. I bet you were fooled. I was as I watched the film. I hope this can show the sophistication of the rendering techniques using ray tracing. Another great indication of what this technology can do is, surprisingly, IKEA. You are currently looking at the IKEA advertising for their furniture. For the past few years, IKEA has switched from taking photos of their furniture on sets to rendering it on computers, and no one noticed. Hardware manufacturer NVIDIA has released hardware to accelerate the ray tracing computation, allowing for real-time use. This has led to a large increase in the technique for producing cutting-edge, real-time graphics in games, virtual reality, augmented reality, and interactive graphics. This has encouraged a lot of people to start learning about ray tracing. One of the largest video game engines, Unreal Engine, has introduced ray tracing as a part of its main rendering pipeline, throwing major support towards ray tracing's application in the video game space. Okay, you've seen all these cool clips playing in the background, and you want to make them too. Here's the simple equation to do so. That is not very easy to understand, and it's not visual. There are a lot of nuances to the process of ray tracing that do not have visual intermediates on their way to the screen. All you can know is the end result. It is hard to understand and visualize the steps associated with what is happening in the scene's physical space. My research has been focused on a revolutionary tool to help computer graphics professors teach ray tracing to students. It is written in JavaScript using WebGL and will run in all common web browsers. This allows professors to demonstrate ray tracing concepts and students to then experience the concepts without having to download the program, install some software, or use fancy hardware. This also will prevent students from just being able to copy code to get the solution to programming assignments. I will now be demonstrating my tool. You can go to this link now or wait till the end of the presentation. My tool can be accessed through any web browser that supports WebGL, which is all the major ones. The top left box contains a real-time viewport of the scene with teaching aids. The top right box contains the same scene ray traced at full resolution through the camera's perspective, allowing a beautiful, detailed view of the output image. The bottom contains a control instruction card in case the user ever needs a reminder. To understand the controls very quickly, my project allows for camera movement within the real-time view. You can use a trackpad or a scroll wheel to zoom in and out. Pressing Shift allows you to move the camera's position. So this allows you to navigate the scene to better understand what is happening. Pressing space on any scene will render the viewport as is. As a quick overview, pressing A allows you to see all of the rays in the scene. Pressing A again toggles only allowing seeing one ray. This is an animated ray to try to help show the direction things are flowing in. Another button to press is R, which resets the viewport camera to the camera's perspective in which the ray is being traced. Pressing space will render all the pixels for the frustum. Pressing minus will decrease the frustum's resolution. Pressing plus will increase the frustum's resolution. But if you want to see the scene again, just press R to remove the colored tiles from the image frustum. Pressing space will then retrace the scene. The user can use the arrow keys to move around and determine which pixel they want to look at. Now, to demonstrate what ray tracing is. The basic problem that ray tracing is trying to solve is, what color should this pixel be? The way ray tracing does this is it starts a ray from the camera's starting position and sends the ray through the center of the pixel, displayed here on the image plane. This then continues through the scene until it intersects with another object. In this case, it is the red sphere. This happens for every single pixel on the image. To better demonstrate this, I've included a shortcut. If you press A, it will display all the rays in the scene. This is all the rays as they traverse through the scene intersecting with objects. Looking at the right-hand side, you may notice that there's no shadows on any of the spheres cast from any other spheres. This blue sphere is in between the green sphere and the light, so a shadow should be cast from the blue sphere onto the green sphere. Ray tracing allows this to easily happen. Going over to scene 2, if we navigate to the pixels which changed, as you can see there's now a shadow on the green sphere, how ray tracing achieved this, a ray is shot from the camera's perspective through the image plane out into the scene. It then hits the green sphere. A new ray is now generated from that intersection point and is shot towards the light source. If any object is in between this intersection point and the light source, this lets the rendering software know that a shadow is where that intersection point is. So that pixel should be colored like it is in shadow. Pressing the number keys allows you to go to a different scene. The purpose of this scene is to demonstrate what happens when there are multiple light sources. As you can see, when the ray hits this point on the green sphere, it is capable of traversing all the way to both lights. This means that both lights will influence the color on that sphere for that pixel. But what happens whenever only one of the lights can be visible? That produces a half shadow, as there's a shadow cast from one light, but there is light still being collected in the scene from the other scene. I hope this is easily demonstrated by the ray intersecting correctly with the light and then hitting the sphere. So there is a shadow cast from the sphere in this light onto the ground. Ray tracing easily allows for what happens whenever both lights are occluded. That creates this dark shadow as there's no light entering the scene. This is easily visualized here as the ray hits the ground and then fails to go to both lights. In scene 5, you can see that there are two spheres with mirror surfaces. Reflections are easy to do in ray tracing. As you can see, a light traverses from the camera's perspective through the center of a pixel out into the scene. When it intersects with a sphere with a reflective material, the light then bounces off of the sphere in the opposite direction of the incoming ray and traverses through the rest of the scene as normal. So in this scenario, it hits the ground plane and then proceeds to try to check if it can reach different light sources. This first ray is able to reach and the second ray is able to reach. That means that this pixel should be brightly colored as it is being lit from both sides. This is the non-shadowed portion in this section of the fully rendered image. This is capable of producing very accurate reflections. As you can see, in the mirror surface, you can see other parts of the scene, such as the red and blue spheres. When the light bounces off of the sphere, it hits the red sphere and then does the light check. You may notice that the other reflective ball is not visible. This is because the bounce has been limited to only one off of the reflective surface. In scene 5, you can notice that we have allowed for more bounces. So what is happening here? As the ray goes through, it bounces off of one reflective surface onto the other and then back. And this repeats multiple times as it goes back and forth between the surfaces until it's able to escape. Once it traverses out into the scene, it then checks which lights it can see. This allows for reflections within reflections. In scene 6, I'm trying to show that ray tracing is capable of working with other shapes that are not primitives. So in this scenario, we have a bunny shape, which is an OBJ file made up of thousands of small triangles. This is a tad bit easier to see within scene 7. Ray tracing operates in a very similar way as it traverses from the camera through the image plane into the scene. It then intersects with the bunny object and bounces back towards the light. It is hard to see at this current resolution of the frustum, so pressing the plus button allows you to increase the resolution. This hopefully helps you find the correct ray to demonstrate what you're trying to see. As the light travels through the scene, it intersects with this bunny's ear and then traverses back towards the light. On its way, it hits the other ear of the bunny. This means that this pixel should be in shadow, as it is. I hope you find this tool helpful and informative as a resource.